So the purpose of this work is to build a workflow to extract ground information from LiDAR point clouds. This information is the key to analyze those structures of mounts systems from under vegetation and characterize them according to different variables: shape, height, slope, diameter, degrees of erosion. Once these objects are characterized, it will be possible to analyze the relation between those morphological characteristics and general topography of the site, analyze the morphology of mounts under vegetation, establish a correlation between the erosion, the mount shape, and the presence of vegetation. And this way we'll see how UAV LiDAR technology allows us to better understand the dynamics of these landscapes. Here we can see the general area of the different flight zones. The place we are studying today is the zone number 4. Some observations can be made on this particular area. We can see the regular distribution of the mounts. The mounts appear to have been colonized by high vegetation. There is a tree or shrub on each mound. Here you can see the red line all around the zone number 4. The surface is about 300 square meters. The yellow line shows the specific area we are working on today. It's a basin surrounded by forest. We want to achieve, on the left, the goal of doing mounts detection and isolate them from the rest of the ground, as we can see on the illustration here. Then we extract useful information for scientific purpose. For this mission, a photographic camera was attached to the YellowScan UAV, together with the LiDAR system. This way, both types of data was recorded at the same time. This gives us the opportunity to colorize the point cloud and easily build a temporary 3D model from photos to help visualize the area. Of course, many times during this user conference, it was demonstrated the limits of photogrammetry in the case of collecting information under vegetation, especially. So the use of LiDAR in this case is the solution. So the acquisition of the LiDAR and photogrammetric data were made by 8 rotors Onyxa UAV at 75 meters altitude. And the data processing will consist in the correction, extraction, and matching of the flight lines trajectories. The extraction of the desired information from the processed data, like digital terrain model and digital elevation model, is used to create thematic maps like slope, surface, diameter, and height maps. Finally, we try as much as possible to automate the data processing workflow through macros and script use. Those point clouds are classified to identify the ground points from vegetation points. We separate high vegetation, low vegetation, and the ground. And now we search for isolating the mounts from the ground. After completing this classification task, we isolate the mounts from the ground in order to obtain a mounts point cloud as well as a ground without mount point cloud. A way to get such results is to use cloud compare and is a scalar field filter. We use this software to clean the point cloud and their densities. For this, we proceed to the following processing with cloud compare. You can see under a cross-section of the point cloud classified. And on the left, it's a mesh generated from the ground without mounts point cloud. And you can see the topography. In blue, you can see the lower altitude, and in yellow, green to yellow, higher altitudes. So this is to illustrate all the data I'm creating and using through this process. From the original point clouds, I get the canopy point cloud, ground point cloud from the classification after I'm filtering, and I get the digital terrain model and the digital elevation model, and then I can get all those results you can see. Here are the results, the digital terrain model I'm generating, and all different maps that are coming from it. So there is the shadow maps, there is a slope map, and because I'm actually working on it, there are more maps coming to get more results. So here, the elevation control lines help to understand visually what is going on here, and we can see clearly the mounts out of the ground. Here are other results. I'm doing the exploitation of those different maps, so I can get surface calculation for each mound. I can get a table to have the surface, to have the diameters, to have the height for each mound. And I also work on creating 3D models of the terrain, the mounts, and also maybe the vegetation, so I can get all the environment made in 3D. So that's it. And I call Doyle.
Okay, thanks very much, Cedric. When Cedric started showing me these data, I've just been completely fascinated because I don't know how to do this stuff, and I really am glad I have some partners who do. A couple of things that this leads me to think about. First of all, I think it shows that drone-borne LiDAR can give sufficiently precise results to be interesting, even in landscapes with relatively little relief. It is even capable of distinguishing the ground from the vegetation, even when the only vegetation is just a short grass cover. And that's important in these areas because as we have seen, this grass cover is very important in the dynamics of the system.
Thank you very much for your fantastic presentation. Actually, I just want to give you some feedback about your project. It's like a landscape art. It's like this is a kind of scientific story behind it, but I feel like this is the art, art of the earth. Yeah, it's great.
Well,
yeah.
We had poetry in the preceding presentation.
That's right.
That first background slide, when I showed that to a group of anthropologists at the Musée Quai Branly in Paris, one was a specialist in Aboriginal art. He says, that's an Aboriginal map of the landscape. So yeah, I like the art part of it too.
Great, yeah, great. Thank you.